So let's look at this first example. We want to find all the critical points of f of xy equal to x cubed plus 6x squared plus y cubed minus 3y squared. So let's see. If I take my partial with respect to x, I'm going to get 3x squared plus 12x. I'm going to set that equal to 0. Then my partial with respect to y, I'm going to get 3y squared minus 6y. I'm going to set that equal to 0. Both of these are not too terrible to solve. I factor out the 3x from the first one, left with an x plus 4. So I either get x equal to 0 or x equal to negative 4. For the second one, I factor out a 3y. I'm left with y minus 2. So in this case, I'm either going to get y equal to 0 or y equal to positive 2. And now I'm going to actually end up getting 4 distinct critical points because each of these x possible things can get paired with each of these y possible things. So I can either have x is 0 and y is 0, or x is 0 and y is 2, or x is negative 4 and y is 0, or x is negative 4 and y is 2. Because as long as x is one of these two things, this first partial will equal 0. And as long as y is one of these two things, the second partial is equal to 0. So no matter which of these 4 points we plug in, both equations will equal 0 at the same time. It's kind of all there is to say that. I suppose we could do the work of classifying them since that's something we're often asked to do. So let's go ahead and classify them as well. So let's find our capital D, which is fxx times fyy minus fxy squared, which in this case is going to be, let's see, fxx is going to be 6x plus 12. Fyy is going to be 6y minus 6. And fxy is going to be 0. So plugging in points, let's see what's happening at 0, 0 first. I plug in 0, 0, I'm going to get 12 times negative 6, which is negative, meaning we have a, got to be a saddle, right? If it isn't more work, that's because it's negative and it's a saddle. If we plug in, let's try plugging in the next one, 0 for x and 2 for y. So we're going to get, let's see, 12. Notice how I didn't multiply this out again, right? I just left the fxx is 6x plus 12, the fyy is 6y minus 6. I'm just plugging in. For the 0, 2, I'm getting 0 plus 12, which is 12. And for y's, I'm getting 12 minus 6, which is 6. That's going to be positive, which means you have a maximum or a minimum. To figure out which, we have to look at either of our second partials. We see that fxx is positive, meaning we're concave up, meaning we have a minimum. Carry on. We look at negative 4, 0. That's going to be negative 24 plus 12, which is negative 12. And 0 minus 6, which is negative 6. That's also going to be positive. But now this time, our fxx happens to be negative, which means we're going to be concave down, which means we have a maximum. And finally, for our last one, negative 4, comma 2, we plug that in, we're getting negative 12 for the fxx part. We plug in 2 for y, we're going to get 12 minus 6, which is positive 6. This also ends up being negative, meaning we have a saddle. So we're going to contrast this with the next example, which is going to feel kind of similar, but not really the same. What I would point out is really the way I would think about this one and the next one is you're essentially pairing any way the first partial could equal 0 along with any way the second partial could equal 0. So I really am saying here either x is 0 and y is 0, or x plus 4 is 0 and y is 0, or x is 0 and y minus 2 is 0, or x plus 4 is 0 and y minus 2 is 0. That's how we're getting all 4 of these critical points. So next example is going to feel kind of similar-ish, but it's also different enough that we should look at it. So let's see here. So here's example number 2. Where'd you go? So our function f of x comma y is equal to 2x squared y minus xy squared plus 8xy minus 7. Again, we want to find, then we'll probably classify them as well. We'll want to find and classify the critical points. So let's go ahead and start taking partial derivatives. So our partial with respect to x is going to be 4xy minus y squared plus 8y equal to 0. My partial with respect to y is going to be 2x squared minus 2xy plus 8x equal to 0. And these look a little dicier than the first ones, right? They're not quite as easy to solve, but each of them do have something we can do. Each of them, we can both factor out something from each of these equations. What can we factor out from the first one? A y, right? Each term has at least one y in it. So we can rewrite this as y times 4x minus y plus 8 equals 0. This one we could factor out an x. And we have 2x minus 2y plus 8 equals 0. And now the same thing we did before is going to hold here. The difference being you can't just get x equals 0 and x equals 4 and y equals 0 and y equals -2 or whatever they were, right? You can get y equals 0 or x equals 0, but here you can just set that whole thing equal to 0 and then have to work with it. So essentially, we're going to pair one of these two factors equal to 0 with one of these two factors equal to 0. So we can either say our first critical point is, well, it's just y equal to 0 and x equal to 0. That's easy enough. 0, 0. For my second critical point, I'm going to set y equal to 0 still, but instead of setting x equal to 0, I'm going to set the other factor equal to 0. So I have 2x minus 2 times y, but y is 0 plus 8 equal to 0. So I'm plugging that y value in for the y spot, and then 2x plus 8 equals 0. So 2x equals -8, so x equals -4. So here we get -4, 0 is a critical point. The third possible pairing, setting this part equal to 0, the 4x minus y plus 8 equal to 0, as well as setting x equal to 0. So I'm going to plug in the 0 for the x over here. I'm going to get -y plus 8 equals 0, or just y equals 8. So the point 0, 8 is my critical point there. And finally, the last one, the most difficult one, setting both of the harder factors equal to 0. So we're setting 4x minus y plus 8 equal to 0, and 2x minus 2y plus 8 equal to 0. In this case, I'd probably choose to just solve this first one for y, because there is a y all by itself already that doesn't have a coefficient that's different than 1. So I'd probably put the y on the other side and say, cool, that's going to be y equals 4x plus 8. And then I can plug that into the other y and say 2x minus 2 times 4x plus 8 plus 8 is equal to 0. And then we can simplify. We get 2x minus 8x minus 16 plus 8 equals 0. So I get -6x minus 8 equals 0, or x is going to equal 8 divided by -6, which is 4 divided by -3, or -4/3. So our final critical point is, oh, I didn't find the y coordinate yet. So I got to plug that back in up here and say, okay, x is -4/3, then y is going to equal 4 times -4/3 plus 8, which is this, -16/3 plus 24/3, which is +8/3. So my final critical point is -4/3, 8/3. And clearly, these ones are a little harder to find, but the idea remains the same. You're taking the factors of the first one, the factors of the second one, just saying, okay, well, in each critical point, one of those factors has to equal 0. The same thing was done before, right? For each critical point, one of these factors had to be 0, and one of these factors had to be 0. The same thing is true over here. It's just a little bit more work to solve it. Well, you should classify them. It's good practice to classify them. So why don't you all find D? I want you all to find your capital D. So capital D, which is fxx, is fyy minus fxy squared. Find it and don't multiply it out. It might make it easier if you could see fx and fy again. All right, let's go ahead and find these things. So here we're going to get fxx is going to be 4y minus, that's it, 4y, right? There isn't anything else for fxx, it's just 4y times fyy, which is going to be negative 2x minus fxy squared, which is going to be, so fxy should be 4x minus 2y plus 8 squared. You can, if you want to, check the other one to see if it's the same. So if you did fyx, it's going to be 4x minus 2y plus 8. Yep, same. Cool. Kind of nice. It's nice to check that they're the same either way. And now we're going to plug in each of our critical points. So we're going to plug in 0, 0 first and see what happens. Interesting. So I'll point out, I already know it's going to be a saddle point. And here's how I know. I saw that I was going to plug in 0 here. This whole part was going to be 0. And then, well, I should say, as long as this part isn't 0, it has to be negative over here, which means it's going to be a saddle. It could be undetermined, right? If it's equal to 0, we actually don't know if it's a saddle or a maximum. But here we're going to get 0 minus 0 minus 0 plus 8 squared. Oh yeah, that's negative 64. That's definitely negative. So we have a saddle. So in fact, that's going to be, I think that's going to be true for any of the ones where one of the coordinates is 0. Because if we do the other one where x is negative 4 and y is 0, I think we're going to get the same sort of result. Because we're going to get 0 for y, and once you plug in 0 for y, the whole thing is 0. Minus 4 times negative 4 is negative 16, plus 0, plus 8. And that's going to be negative 8 squared, which is still negative 64, I should say. Negative 8 squared is 64, and then it's the negative of that. So it's negative parentheses, negative 8 squared. Still negative, still a saddle. Look at this next one. Plugging in 0 for x and 8 for y. I bet we're going to get the same result. So when we plug in 0 for x, you get 4 times 8 times negative 2 times 0. Oh, that's 0. And then you've got 4 times 0 minus 2 times 8 plus 8 squared. And we again get negative 64. It is not uncommon for all these values to end up being either the same value or the opposite value of each other. It's just kind of a thing that happens a lot. I don't exactly know why, but there's probably a good reason for it. And finally, wow, that's an upside down exclamation point. Okay. And finally, the fourth one here, where the values were interesting, negative 4/3 and positive 8/3. Let's see what happens here. So when we plug in negative 4/3, we're going to get negative 4/3 for x. So we're going to get negative 2 times 4/3, negative 8/3. And then 8/3 times 4 is going to be 32/3. Sorry, I did that kind of backwards. I don't know why I did that backwards. I should have just plugged in the y in the first spot instead of, sorry, I was just looking at plugging in x. I did that very kind of weirdly. Apologies. And then, I feel like I'm making a mistake somewhere. I'm missing a sign. So let me try again, just to make it so it's a more typical way of doing it. If I plug in the 8/3 for y, I'm getting 32/3. If I plug in the negative 4/3 for x, I'm getting positive 8/3 instead of negative 8/3 which I had before. That looks better. Minus 4 times negative 4 thirds, so negative 16 thirds, minus 2 times 8 thirds, minus another 16 thirds, plus 8, which I'm going to simplify to 24 thirds. So here's what we've got. We have 32 thirds times 8 thirds minus negative 16 minus 16 is negative 32 plus 24 is negative 8 thirds squared. Okay. I want everyone to look at that. 32 thirds times 8 thirds minus negative 8 thirds squared and decide in your head, is that whole thing positive or negative? In your head. I'll give you 10 seconds. Why in your head? Yes, it is positive. And the way I'm really thinking about this, I know that 32 times 8 is bigger than 8 times 8. I'm really ignoring the negative there, right? The 3's on the bottom don't matter. They're going to work out to be the same. But this 32 times 8 is for sure bigger than this 8 times 8. So it's got to be positive. And now that I've written things in the correct order, this fxx here, right, that is fxx. It is also positive, meaning we're concave up, meaning we have a minimum at this point. So yeah, finding, classifying. They're usually not quite this bad, but I wanted to show you some that were, I think, kind of at the outer limit of how bad they get. I mean, they can get much, much worse, but usually in this class, we're trying to make them so they're not too terrible. Okay. Let's continue on in the same vein, but with a few more optimization problems, because we only got to do one last time. I do think they're worthwhile. Yeah. And unfortunately, a lot of them are just kind of ugly. The numbers are often not super duper nice. That's just something we have to be prepared to deal with. So let's look at this first optimization problem. So find the point on the plane x plus y minus z equal to 1 that is closest to the point 2, 1, negative 1. I will point out that 2, 1, negative 1 is not on the plane, right? If you plugged in 2 for x, 1 for y, negative 1 for z, it would not, 2 plus y minus z would not equal 1. Otherwise, it wouldn't be a very interesting question, right? If the point was on the plane, then itself is the point that's closest to that point on the plane. So it's really not a good question if the point's on the plane. So we could draw a picture, although I don't think we really need to, but I'm going to draw a picture for you anyway, just so you can kind of see it. So here's my x-axis, my y-axis, and the bottom half of the z-axis. And then this plane has intercepts at x equal to positive 1, y equal to positive 1, and z equal to negative 1. So there's part of the plane there. And then this point, 2 in the x direction, 1 in the y direction, and negative 1 in the z direction. So this point, like down here, we're trying to find what point on this plane is closest to this other point, 2, 1, negative 1. Or phrased in a way that makes it so we can actually do something, we want to minimize the distance between the point and the plane. So our goal is to minimize the distance between the point 2, 1, negative 1, and some point that we don't know, let's call it x, y, z on the plane. So we're trying to minimize the distance, which we also use a capital D for, unfortunately. It's just typical. Between these 2 points, which is the square root of the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared. Now, there's one thing we almost always do with a problem like this to make it easier from the get-go, and that is we drop the square. Or what we really do is we say, well, if you're trying to make this quantity as small as possible, you have to make the thing inside the radical as small as possible, right? The smaller the inside is, the smaller the output's going to be. So if we make the argument of the radical as small as possible, we will have minimized the distance. Another way of saying this is we're going to minimize the square of the distance. So really, instead of doing this, we're going to minimize the distance squared, which is equal to x minus 2 squared plus y minus 1 squared plus, I'm going to write this as z plus 1 instead of z minus 1 squared. Something to remember is that the thing you're trying to optimize shouldn't ever be equal to a number yet, right? We don't know what it's equal to. If we did, we'd be done. We would know the minimum distance. So this thing we're trying to optimize, we're just a function of usually 1, 2, 3, one too many variables. And then there should be some constraining piece of information. In this case, we know that x, y, and z have to satisfy this equation because that point has to be on that plane. So our constraint here is going to be that x plus y minus z is equal to 1, or isolating z is equal to x plus y minus 1. We're going to take that, and we're going to substitute that in for z right there. So that then we can write the thing that we're trying to minimize as a function of just two variables. So now we're trying to minimize distance squared as a function of just x and y, which is going to be x minus 2 squared plus y minus 1 squared plus x plus y minus 1 plus 1. Let's not write that squared. Right, I plugged in the x plus y minus 1 there, but then the minus 1 and the plus 1 at 0. Okay. Now what? We have the thing, we're trying to minimize it, function of two variables. Yeah, with the partial derivatives, yes. Right, you could write them kind of grossly as d squared x and d squared y. So let's see, so d squared x, the partial of the distance squared with respect to x is going to be 2 times x minus 2 plus 2 times x plus y times 1, if you like. Similarly, for the partial of d squared with respect to y, it's going to be 2 times y minus 1 plus 2 times x plus y. Yeah. So let's multiply it. So it looks like we're going to have two equations of lines again. And so we're essentially going to end up finding where these two lines cross each other. If I simplify this, I've got a 2x plus another 2x. So I've got a 4x. I've got a 2 times y. And I've got a 2 times negative 2. Down here, I've got a 2y plus 2y. So I've got a 4y. I've got a 2x. And I've got a 2 times negative 1. Again, solving a system of equations like this is really something you can do in any way you prefer. You can either solve for x or y in one of these and substitute in the other one, or you can multiply one of these equations by a constant, add to the other one to eliminate. So you can either use substitution or elimination. Either way is fine. Do whatever feels most comfortable to you. Here, I'd probably choose substitution. So I'm going to take this equation here since I can divide. Right, what I'd probably do first actually is divide everything by 2. I'm going to say this becomes 2x plus y minus 2 equals 0. And this one's going to be 2y plus x minus 1 equals 0. Isolate y in that first equation so that y is equal to negative 2x plus 2. And plug it in for y in the other equation. So 2y plus x minus 1 equals 0. I'm going to take this and substitute it in for y right there. So I have 2 times negative 2x plus 2 plus x minus 1 equals 0. And finally, multiply it out. Negative 4x plus 4 plus x minus 1 equals 0. You get negative 3x plus 3 equals 0, which ends up giving us that x equals 1. Go back over here, find the y value. You get y equal to negative 2 plus 2, so y is going to equal 0. And then go back and find the z coordinate as well. we had that everything is on the plane z equals x plus y minus 1. So if y is 0 and x is 1, I'm going to get 1 plus 0 minus 1, which is 0. So the coordinate of my point that is closest to the point 2, 1, negative 1 is 1, 0, 0. Let me see one thing. So I might have skipped a step. Not that we have to go back. I might have skipped a step in saying it was the closest. How do we actually know it's the closest? How do I know this is a minimum and not a maximum? Maybe I found the point on the plane that was furthest away. Well, one answer to that question that's kind of a little hand wavy is that this plane extends in kind of forever directions, right? So you couldn't really find a point on the plane that's furthest away from this point because you could just find another point after that that was further away. So it's definitely not a maximum distance. So that's one way you could kind of just say, well, then it has to be a minimum. Or we could do the checking, right? We could find our other capital D, fxx, or sorry, yeah, let's just call it fxx, even though I know I called it d squared before. So we're going to find this and we're going to check our critical point. So looking back at our first partials. Oh, look, there they are right there. Here's my first partial with respect to x. It's 4x plus 2i minus 4. My second partial is going to be just 4. For fyy, my second partial is also going to be 4. And then for fxy, it should be 2 either way. And look, it's going to work out great. That's going to be 16 minus 4, which is 12, which is positive. So it's either a max or a min. But since we note that both fxx and fyy are positive, that means we're concave up, which means it has to have been a minimum. So yes, we get minimum distance at the point where x equals 1 and y equals 0, and also z equals 0. But that wasn't part of really showing it was a minimum. Kind of a lot of work, right? So these optimization problems, a large portion of the battle is just the setup and writing the equation for the thing you want to maximize and the equation for the thing you want to, that's your constraint, and then getting the thing you want to maximize and down to 2 variables. And then finally, once you're there, then taking the partial derivatives, finding the critical point, testing to make sure it's the thing you're supposed to have. Ugh. Okay. I think there was something else I wanted to say here. No, I guess not. How much time have we got? Oh, we got time. So let's look at 2 more examples, and then if we're done with them before the end of the time, we can call it a day. But that seems unlikely with how complicated. They're not super complicated. They just, again, they take a lot of setup. Let's look at, yeah, this next one. Yeah, I think this is good. Have I lost my numbers? Maybe. Yep. Also, you're always welcome to ask questions. So here we want to find the dimensions of the least expensive rectangular box where the material for the top and bottom costs twice as much as the material for the sides. So far, I haven't given you a constraint. So if we read this question just as, all we know is we're trying to maximize something, or we're trying to minimize the cost, and we kind of have a way of setting up the equation for the cost. And we want the volume to be 16 cubic feet. Now we have a constraint. So I would draw a picture. Draw a typical box shape. When you're drawing a shape that is supposed to be a box, we shouldn't make any assumptions about any sides being equal to any other sides. So even though I've kind of drawn this in a way where it kind of looks like this length here and this length here could be the same, we definitely shouldn't assume that. So we're going to label the sides of the box. I typically label this side X, this side Y, and this side Z. So we're going to set up two equations. One's our thing we're going to minimize, and one's the thing we're going to is our constraint. So again, we're not setting up the equation for the surface area, although I'll point out the surface area equation would be the bottom area, which is X times Y, plus the top area, which is X times Y. So there's two X times Y's. The right area, which is Y times Z, and the left area, which is also Y times Z. And finally, the front area, which is X times Z, and the back area, which is also X times Z. That would be the surface area equation. But I want a cost equation where we're saying, oh, this bottom and top part here, this costs twice as much. So the problem is they didn't tell us how much it costs. Well, it actually doesn't matter. We just have to assign some numbers. So we could just say, well, cool, these parts are going to cost $1 per square foot, and these parts are going to cost $2 per square foot. So we need to multiply this part by twice as much as whatever we multiply this part by. And 2 and 1 are the logical are the easy choices. There are other logical choices. So our cost equation is going to equal 2 times 2 times X times Y plus 2 times Y times Z plus 2 times X times Z. And it wouldn't really matter if we multiplied this by 2 and this by 1, or this by 8 and this by 4. It's still going to have the same multiplication factor, which is still going to lead to the same partial derivatives being set equal to 0, just with a different constant factored out of it. But it's not going to matter as far as finding the critical points. As usual, the thing we're trying to minimize has more variables than we know how to deal with. So we have to have a constraint. Our constraint, which will make it look different than the cost, our constraint is that the volume, which is X times Y times Z, we want that to be equal to 16. Then we do the typical thing. We take our constraint, we isolate the variable, we plug that into that variable in the other equation, and we move forward. So I'm going to usually isolate Z unless it seems like that's the wrongest choice to make. Or like isolate the one that's easiest. Here, it doesn't matter, X, Y, or Z, it's all kind of the same. So Z is equal to 16 divided by X times Y. And then we're going to plug that in for Z here and here. So here and here, not there and there. So in our cost equation, now, which will be dependent just on X and Y, I have 2 times 2xy, which is 4xy, plus 2 times y times what we're plugging in for Z, which is 16 divided by xy, plus 2 times x times 16 divided by xy. And I definitely think it's worth our time to simplify this before we start taking partial derivatives. So simplifying, our cost equation is equal to 4xy. The y will cancel here. 2 times 16 is 32. Since I'm going to take a derivative, instead of writing 32 over x, I'm going to be better off writing 32 times x to the negative first. Similarly, this should be 32 times y to the negative first. Now let's take the partial derivatives, set them equal to 0, find the critical points, test them, make sure it's a minimum. Okay, so partial derivatives. Our cx is 4y minus 32x to the negative second. That doesn't seem good. And our cy is going to be similar. It's going to be 4x minus 32y to the negative second. Well, look, we have this symmetry thing happening again where we're pretty confident that x and y are either going to be the same or they're going to come in like conjugate pairs where you have like 3,7 and 7,3. Okay, so here's what I would do. I would write this as 4y equals 32 divided by x squared. I'd probably divide both sides by 4 and say y is equal to 8 divided by x squared. And then we really should plug it into the other equation, which is not my favorite way of doing this, but it's the way you avoid any unnecessary errors. Yeah, is that really the way you want to do this? I think it is. So this equation, which is 4x minus 32 over y squared equal to 0. we're now going to plug in 8 over x squared or y squared. Be 4x minus 32 over 8 over x squared equal to 0. Okay, let's make this a little bit better. That's 4x minus, let's see, 32 divided, be careful, James. I got to square this part first. We got 32 divided by 64 over x to the fourth, which really becomes 4x minus 32 times x to the fourth over 64. So I've got 4x minus 32 over 64 is 1/2 x to the fourth. We're almost there. We can factor out an x. And we're left with 4 minus 1/2 x cubed, 0. So we're either going to get, since I said 1/2, x equal to 0, or 4 minus 1/2 x cubed equal to 0, which becomes 4 equal to 1/2 x cubed, or 8 equal to x cubed, or x equal to 2. Whew. We know one of those doesn't matter at all. X equal to 0 doesn't tell us anything. Well, in fact, x equal to 0 actually isn't in the domain of this function. Because if you look back over here at the original function, after I wrote it in terms of x and y, we're dividing by x and y here. So x can't equal to 0, can't be the domain. Also, if x is 0, you can't get a volume of 16. Also, if x is 0, it doesn't make any sense. So usually when we talk about dimensions, 0 is not the right answer for any of the dimensions. So we're just going to ignore that. We're going to say x equals 2. We're unsurprisingly going to get y equal to 8 divided by 2 squared, which is also 2. And then if we go back and find our z is 16 divided by x times y, which is 16 divided by 2 times 2, which is 16 divided by 4, which is 4. So the dimensions appear to be 2 feet by 2 feet by 4 feet high. Technically, we should probably check to make sure it's a minimum, which never feels fun after you've done all this work. I mean, okay, fun. Some of it, but yeah, it really does not feel fun. So if we look at our first partials up here and take our second partials, okay, so our capital D, yeah. So CXX is going to be positive 64 times x to the negative third, or 64 over x cubed. CYY should be the same thing for y. It should be positive 64 times y to the negative third, or 64 over y cubed, minus CXY, which is easily 4 squared. And if we plug in our critical point, 2 comma 2, we're going to get 64 over 8 times 64 over 8 minus 16, which is certainly positive. It's 8 times 8 minus 16. And then, as usual, we can see that the thing we're looking at is the right thing it's supposed to be. This is positive, concave up, minimum, as we wanted it to be. So yes, these dimensions minimize the cost.
I have a quick question.
Yeah.
So if we checked and we found out that like we were wrong, it doesn't minimize the cost, what would we do then?
So the reality to that question is we're never asking you the question in a way that you don't get the thing we're asking for, unless someone's made a mistake. So if someone says, find the things that minimize this thing, and you find something that doesn't minimize it, either the person asking the question asked it wrong, or you might have made a mistake, or I might have made a mistake finding or evaluating the capital D thing. But yeah, we almost always with these questions, you're only ever going to get one critical point, and that critical point is going to minimize if we're trying to minimize, or maximize if we're trying to maximize. Rarely, and this is more really in 17A, you might have functions of one variable where you actually get multiple critical points, and some, like there's one problem where it's like you're trying to swim across the river and then get to some point down the way, and like you can either swim straight across and then run, or you can like swim diagonally and then run less far, and you have to like figure out which way minimizes the amount of time for some reason, and there end up being like more than one critical value, and you have to like test each one to see which one actually does take the least amount of time. But that is kind of a rare exception. Most of the time, one critical point and it does the thing you're trying to do. So yeah. So that shouldn't happen, hopefully. Let's see here. Let's look at the last one that I've got on my mind and see if we really want to do it. Let's set it up. We won't finish this one probably, but we will set it up. This is kind of a classic optimization question that used to be true with real numbers. I don't know if it still is, but here's the setup. Find the dimensions of the largest box. When we say box, we mean like a rectangular box by volume. So we want the most volume that can be mailed under the U.S. Postal Service requirement that the length of the box plus the girth of the box, or you can think of it as like the circumference of the box, is no more than 108 inches. So here's what we're kind of trying to see. We have this box again. And at least for our purposes here, we should imagine it being like much longer than it is around, or it should be clear which side is like the long side. So, right, you wouldn't want to measure the girth this way, because then you'd be taking your longest side twice, which you don't really want. So it makes the most sense to measure the girth around this way. There's your girth. And then the length is going to be the longest side. So if we label things in the typical way, where this is X and this is Y and this is Z, well, we're trying to maximize volume, which is just X times Y times Z. Our constraint is that the length plus the girth, so the length is Z, the girth is X plus Y plus X plus Y, or 2X plus 2Y. We want that to be less than or equal to 100 inches, but if we're trying to get the most volume, you don't want to use less than the constraint gives you, so we're just going to set this equal to 108. And then it's the usual thing. Isolate a variable, plug it into the thing. This one is less ugly than the previous one. So here, I would still pick to isolate Z because it's kind of the odd man. I don't want to divide this equation by 2 if I don't have to. So I'm going to say isolate Z. It's 108 minus 2X minus 2Y. And then we're going to plug that into our volume equation. So volume now, depending on just X and Y, is going to equal X times Y times 108 minus 2X minus 2Y. It definitely makes sense to multiply this out before we start taking derivatives. I'd rather not use the product rule if I can help it. So we're going to get 108xy minus 2x squared y minus 2xy squared. My x partial is 108y minus 4xy minus 2y squared. My y partial is 108x minus 2x squared minus 4xy. And we see the same sort of thing we saw for the second problem we started out today, which is that each of these you can factor something out. So we can rewrite this one as y, and let's say 2y times 54 minus 2x minus y. And this one is 2x times 54 minus, 54 minus x minus 2y. And we know 3 of the 4 critical points you could find are not valid in that you're going to have x and y both 0, or y equal to 0, and this equal to 0, which means x is going to be 54, or x equal to 0, and this equal to 0, which means y is going to be 54, or the actual way we're going to get the critical value, which is by setting each of these parts equal to 0 and finding the solution where x and y are both not 0. Because again, x equal to 0, y equal to 0 just doesn't make sense here. So to do that, yeah, we have enough time. If we set each of these equal to 0, and I'll solve this the other way. Even though you could totally isolate y or x really easily here, I really do kind of prefer the elimination method. So if I multiply this equation by -2. I'm going to get -108 plus 2x plus 4y equal to 0. And then my other equation from up here is 54 minus 2x minus y, 0. And then if we add those equations together, -108 plus 54 is -54. 2x plus -2x is 0. And 4y plus -y is 3y. Solve for y, you get 3y equal to -54, or y equal to +54. So there I was like, well, that's not going to make sense. It clearly must be positive, I'm right, because I can't get y being negative. So y is going to equal 18. And then if you plug that back, so the only downside to doing it elimination style is then you have to go back and like plug it into one of the equations that isn't solved for x already. So then you can plug in, I don't know, like here, 54 minus x minus 2 times 18 equals 0. And shock of all shocks, 54 minus 16 is 18 is going to equal x. So you get x equal to 18, you get y equal to 18, and then plugging back into your original isolated constraint up here, you're going to get z equal to 108 minus 2 times 18 minus 2 times 18, which is 36. So the biggest box by volume that you could mail is 36 inches long by 18 inches by 18 inches in width and depth. Kind of neat. So 3 feet by 1.5 by 1.5. And we won't check to see it's a maximum. It is a maximum. You can check on your own. And it's not that hard to check, right? You can totally easily find the VXX, VYY, and VXY, and then check to see that D at this critical point, 18, 18, is in fact positive, and the second partials are negative, meaning you have a maximum. All right, it's 1 o'clock. I'll stop.